Hello and welcome again to my Physics Online video lecture supplement series. In today's video, I'm going to continue my lecture set number 4, covering electrical capacitance and dielectrics for the Physics 2 classes. We are continuing this lecture now with part 2, which covers the dielectrics part of this topic. And basically, a dielectric is any kind of insulating material that you can insert into a capacitor. So basically a dielectric means it's an insulator. And what happens is when you insert the insulator between the two plates of your capacitor is that you reduce the voltage drop across the capacitor by some factor 1 over kappa, where kappa is some constant for the material called the dielectric constant, so unitless quantity. Now when this happens, and assuming that the capacitor is not hooked up to a battery or other power supply that could supply it with additional charges, the charge on the capacitor has to remain constant. So the charge on the capacitor stays constant. The voltage drop across the capacitor is reduced by a factor of 1 over kappa. What this means is that the capacitance of the capacitor is given by kappa times whatever the charge and over voltage would have been without the dielectric material. So the capacitance is the charge that the capacitor holds under the conditions of having vacuum between the two plates divided by the voltage that would have been between the two plates when it's charged, times this factor kappa. So for a pair of parallel plates, the capacitance looks like kappa times epsilon naught times A over D. So in other words, by inserting the dielectric between the two plates, you actually are increasing the capacitance of the capacitor. And you're doing that by having a smaller voltage drop per unit charge on the capacitor. So the capacitance still remains the charge divided by the voltage that you have to put across the capacitor to get that charge. It's just that now that capacitance has been increased by a numerical factor. The result of that, incidentally, is that the potential energy of the capacitor has to decrease. And you can see that by seeing that you're decreasing the potential, therefore you're decreasing the potential energy. Recall in any case that the potential energy is given by 1/2 of the capacitance times the change in voltage squared. So we increase the capacitance by a factor of kappa, we've decreased the voltage drop by a factor of kappa, therefore we've decreased the potential energy by a factor of kappa, because we have a kappa squared over kappa a kappa over kappa squared effect, and that means that we have a 1 over kappa effect on the potential energy. There's a maximum potential difference which a capacitor can maintain with a dielectric in it before you get what's called dielectric breakdown. And basically what happens in dielectric breakdown is that you get the equivalent of a spark. So in this case, the dielectric in question is air. So these two are acting like capacitors. You get enough of a voltage between the two, you get enough of an E field strength between the two, and the air starts breaking down and you get sparking like this, where some electrons are jumping from one plate to the other, or one lead to the other. So basically what happens is you have some maximum potential difference which you can have between the two plates of the capacitor before this happens. And since the plates have a given separation, this is really equivalent to saying that for that separation, there's a maximum electric field which can exist between the two plates before charges start moving from one plate to the other via dielectric breakdown. And this maximum electric field strength is called the dielectric strength of the material. And so one obvious example of this is shown here in this diagram to the right. Another example is found in lightning. The two plates in question are effectively the clouds and the ground, and so the dielectric in question is air. Alright, so this table actually gives some dielectric constant values and also the dielectric strength, meaning the maximum E field that you can have for a given separation between plates, is equivalent to saying here's what the maximum voltage is for that separation. And the air is what's commonly found between two plates if there is no dielectric in between them. Vacuum is the perfect 1.000 kappa basically means this is what we calculate the simple case based on. So far our calculations have assumed that there's vacuum between the two plates. Air, you can see, is very close approximation. The difference being that there's not really a dielectric breakdown for vacuum that would fit on this chart. There is such a thing for air. And so you can see that there's a few advantages to using a different dielectric than air. There's also some advantages over using vacuum. In any case, every one of these dielectrics, beyond air and vacuum and beyond other types of gas, you could put just nitrogen into, you could put carbon dioxide, that kind of thing. You're going to have also a low dielectric constant. The upsides to using some dielectric are that you increase the capacitor's capacitance, which effectively means that you increase how much charge you can store on a capacitor for a given voltage drop across it. Compared to air, just about everything on this list has a greater dielectric strength. So compared to air, you can put a larger voltage between the two plates, and that also means you can store more charge. And then everything on here, including to some small extent air, but especially all of these solids as compared to vacuum, actually will lend some mechanical strength between the two plates if the two plates are close together. In other words, you don't have to worry about the plates, for example, bending so that contact is made and you short out your capacitor. If you have something like paper or fused quartz or silicon oil or any of these things, you lend a little bit of strength to those two plates to actually physically hold them apart even when there's a large charge on them. So let's look at a few examples of dielectrics from what we've discussed so far. All right, first of all, we have a capacitor which is fully charged and has a voltage of 10 volts and a charge of 1.00 millicoulombs with air filling the space between the parallel plates. So we want to know what's the capacitance in air and what would it be underwater. So C is basically going to look like Q over delta V. And for air, we're told it's already fully charged, so these actually will work for the Q and the delta V for air. So this is 1.00 times 10 to the minus 3 coulombs divided by 1.00 times 10 to the 1 volts. And so this gives us 1.00 times 10 to the minus 4 farads. Okay, what about when we place this thing underwater? Basically, to answer that, we can pull up this table, and we notice that water has a dielectric constant of 80 and air has a dielectric constant of approximately 1. Therefore, we could write something like C water is equal to kappa water over kappa air times C in air, where this thing that we found up here is C in air. So this is approximately equal to 80 over 1.00 times 1.00 by 10 to the minus 4 farads. And so the capacitance in water would be approximately 8 times 10 to the minus 3 farads, or 8.0 millifarads. Our next example is how much work do we need to do on the capacitor that we just described in order to remove it from the water. So to do that, you can use work is equal to negative delta U, where delta U is given by the equation for potential energy in a capacitor. We could call it U sub E for electric field, or U sub C for U for a capacitor. And recall that this is given by 1/2 of Q times delta V. And since we basically are assuming that this thing has been charged, there's two possibilities. It could still be plugged into a battery or some other power supply, some other source of charges, or it could be unplugged from the battery. And what happens actually depends on which of those two situations we have. If it's plugged into a battery, then the voltage is going to remain constant across it, and instead the charge is going to change. If it is unplugged from a battery, then the charge remains constant and the voltage drop changes. But you can see that basically either way, you're going to end up with a factor of 1 over kappa difference for this equation. So basically we could say U underwater is 1/2 times Q naught delta V naught over kappa. And U for E in air is going to be 1/2 of Q naught times delta V naught. So the work done in this case has to be the change in these two energies. You can see that since kappa is 80 in this case, that the amount of work that's going to be done here is you're doing work to remove this thing from water. So the amount of work done is going to be 1/2 Q naught delta V naught times 1 minus 1 over kappa. So basically it's 1/2 of this vacuum potential energy times the difference between vacuum potential energy and potential energy under the water. So what that ends up looking like, basically 1/2 times Q naught again was 1.00 by 10 to the minus 3 coulombs. Delta V naught again was 10.0 volts, and we have 1 minus 1 over 80. So you multiply these things together, and what you end up getting is basically about 0.0049375 joules. So in this case, the work done is not terribly much work. With that said, the fact that you have to do work to remove it from water also implies that if you take a pair of parallel plates like this, let's say that you've got the one side is positively charged and the other side is negatively charged like so, And let's say that you just let it rest with some dielectric slab partially filling this space. And maybe the dielectric slab is something like this. What's going to happen is, because it's a lower potential energy for this slab to fill the space entirely, the capacitor is going to tend to draw the slab up into itself. And that includes not only a slab, but also, if you have water, a column of water can be drawn into this, in between the two plates. Okay, so now we ask, how close together can the plates of this capacitor be before it creates a spark in air? Given, again, that this is the above capacitor, so given that there is 10 volts as a potential drop from one plate to the other. So we need to pull this table back up, and you see that the dielectric strength is 3 times 10 to the 6 volts per meter for air. So we sometimes call that E max because it's the maximum voltage electric field that we can sustain before dielectric breakdown occurs. So 3 times 10 to the 6. We're given that the voltage drop is actually 10.0 volts, and we know that E is delta V over delta X. So put all this together, and what you get is that delta X minimum is given by delta V divided by E max. So that is going to be 10.0 volts divided by 3 times 10 to the 6th volts per meter. That's the field strength units. And so this right here is going to give us approximately 3.33 repeating. So we'll just call it 3 microns, or 3 times 10 to the minus 6 meters of separation. Oops, this actually is delta X min. So that is the minimum separation between the plates before you start to break down the air between the two plates. Okay, last short example is, how much voltage can we actually put across this capacitor if the plates are rather far apart, say 0.1 millimeter apart? Well, basically you use the same general equations. Again, E max for air, 3 times 10 to the 6th volts per meter. Now we use E is delta V over delta X, and now we're trying to solve for a V max. So delta V max is equal to E max times delta X. In other words, the maximum voltage between the two is given by the dielectric strength of the air times the separation between the two plates. So this is 3 times 10 to the 6th volts per meter times 0.1 millimeter, which is the same as 1 times 10 to the minus 4 meters. And so this means that the maximum voltage that we can put on this thing is actually about 300 volts. And if we exceed that, then dielectric breakdown will begin to occur in the air. One consequence of this limiting factor of dielectric breakdown is to be found in a specific physics application, which is in conventional accelerators, be they SLAC, which is what's pictured below here, or the Tevatron, or the current largest, which is the Large Hadron Collider. All of these have a limitation to how large of an acceleration they're able to obtain. Basically, the fields used in these accelerators are limited to about 10 to the 7th volts per centimeter. And so if you want to obtain a very, very large particle energy, you end up having to build a very, very large accelerator. So pictured again here is the Stanford Linear Accelerator, and this long thing right here is actually the main acceleration beamline. And you can actually see here's the road in that area. It kind of passes overhead over this thing. The scale is about 3 kilometers long. So from here to here, approximately 3 kilometers. For the LHC, the largest and most expensive right now, it's more of a circular path than a linear one, but you have a 27-kilometer circumference. And the LHC certainly cost billions of dollars to build. So all of this is caused by needing to stay safely below the dielectric breakdown limit for the materials used in constructing these devices. There is actually a way of getting around dielectric breakdown as concerns particle accelerators, and this is to use something like a Wakefield accelerator. And so how that works is that you send either a laser pulse or a pair of lasers that are at different frequencies, or a cluster of charged particles into a plasma. And what that basically does is it sets up an oscillation, really sets up a wave or a series of waves behind that and slightly in front of that pulse. All the electrons in the plasma kind of get expelled from the region where the pulse is traveling through, be it a laser pulse or be it a charged cluster. And then that leaves the positively charged ions sort of on axis. And so you have this evacuated area where all the electrons have been expelled. There's a very large electric field then because of this charge separation, and so you get this wave behind it. And you can then inject other charged particles into this, or as the case often is, you get self-injection. And these injected particles get accelerated by the field of these waves in a very similar manner actually to a surfer getting accelerated by a wave at the ocean. It sort of rides down the potential curve of the wave. And what happens here is that these accelerators are able to sustain very large acceleration gradients. 10 to the 9 volts per centimeter, that's a gigavolt per centimeter. And in fact, one of these has been used, a plasma Wakefield accelerator has been used to double the particle energy output from the Stanford Linear Accelerator that I showed on the previous slide. Only this doubling occurred in a space of about 84 centimeters. It was a little under a meter. So compare that 1 meter versus 2.7 kilometers, and you could see why these might be a preferable method if we can scale them up to comparable energies with the larger accelerators. Now, scaling them up to those larger energies on their own hasn't happened yet. There's a lot more engineering and a lot more advances in the science that have to happen first. In fact, Stanford Linear Accelerator is still a very nice facility, still very cutting-edge research, and this doubling wouldn't have been possible without also having the Stanford Linear Accelerator. The Stanford Linear Accelerator, for what it's worth, without doubling, has observed up to about 40-some GeV as the particle energy. That's giga-electron volt, to use a unit that I introduced in the last set of lectures. The record right now that I know of for the Wakefield-based accelerators without using a standard linear accelerator or Tevatron or what have you to seed the Wakefield, the record is a little bit over 2 GeV. So maybe an order of magnitude smaller still than the Stanford accelerator, but still quite high. And that record actually is held by a research group at the University of Texas in Austin, a collaboration between Dr. Todd Dittmeyer and his petawatt laser and Dr. Mike Downer and his laser wake field acceleration group. I guess I should say for disclaimer here that one of those two men was my advisor for my PhD thesis, and the other one actually sat on my dissertation committee. So I wasn't necessarily involved directly in that particular project, but I do have connection to those folk. What these accelerators are used for right now, these tabletop ones certainly, are primarily for research purposes, but they could in principle be used, and in some cases are used, to generate charged particles for anything from radiation therapy to deposition sources to coherent X-ray light sources. To pick a more mundane use for dielectrics, not dielectric breakdowns, but dielectrics themselves, you may or may not have before attempted to find the upright beams in the wall of your home, what are called the studs. Not only the upright beams, but the cross beams. Basically, the wood support frame of your wall is called the studs. And it's useful to know where these are because if you want to actually suspend anything from the wall, anything that's going to have weight-bearing capabilities, it's generally a good idea to anchor it into the stud. And so one way of doing that, of course, is that you can sort of knock on the wall and listen to see if it sounds more hollow or more solid. And where it's more solid, that's where the studs actually are located. But sometimes you want a double check for that. And I can say this having been a person who's lived in some shoddily built apartments before. The studs were sort of thrown up any old place. You kind of do the knock test and then you don't believe where you found the studs because you'll find two that are 6 inches apart and then the next two are 30 inches away. Be that as it may, the way that these stud finders work is that they have a pair of capacitor plates marked in blue in this diagram. They're actually not parallel, but instead are more side by side. And when you place something like a piece of wood below them, it's equivalent to placing a dielectric into the capacitor. And so that is going to change the capacitance of the two plates. Since there is a constant voltage drop across them, it's also going to cause there to be a difference in charge on them, so it basically causes some current to flow to or from the two plates, and as a result you get a little light that lights up and maybe a little buzzer that buzzes, and it tells you, okay, there's a stud underneath here. And it's just basically using a change in the capacitance of the stud finder. That's also incidentally why when you first turn them on, they often will light up and make a buzzing sound, is because when you first turn them on, you get some current flowing. Then the capacitors are charged. Then you stick a dielectric beside, which is equivalent to sticking it between the two, and so some more current flows. Alright, I want to talk now about electric dipole moments because this ties in basically to the explanation of how dielectrics ultimately work to increase the capacitance of a capacitor. So let's begin with the simple electric dipole again, which is pictured here. Simple electric dipole basically involves a positive charge and a negative charge of equal magnitude separated by some distance L. And we can define what's called the electric dipole moment, which is sometimes given by the vector P, and it's directed from the minus charge to the plus charge and has a magnitude given by P is equal to L times Q. So the distance between the two charges times the magnitude of the charge gives the dipole moment. And these dipole moments tend to align themselves along electric fields. So you can imagine if there was an electric field line here, then the Q, the plus Q, is going to want to move along the field lines. The minus Q wants to move away from the field lines or against the field lines. Basically, that's how the accelerations will work. Ultimately, this thing will align so that the field points in the same direction as this dipole vector. So what happens if you actually put a dipole in an electric field such that it's not aligned with the field? So here we have a dipole. Here is the dipole moment. Here is plus Q. Here is minus Q. Field is moving from left to right. And what basically happens is that each of these two forces is going to experience a force of equal magnitude, but in opposite directions. So each charge is being pulled by the electric field, but in an opposite direction from the other charge. So you can see from this diagram, if you were to imagine that this was a rigid object, what would happen is that you'd have a torque on the rigid object. So the rigid object would want to spin like this. Same thing works if you have a dipole. There's a torque, in this case, in the clockwise direction. And so what will happen is that the dipole will start rotating in the field until it has eventually aligned itself with the field. It may overshoot and then be torqued back and overshoot and torque back, so you could actually get a sort of harmonic oscillator with this. But ultimately, the molecules are going to end up, or the dipoles, are going to end up aligning themselves such that the positive is here and the negative is somewhere over here. They may be slightly stretched, but when they are aligned in this way, there is no net force and there is no net torque on the dipole. And we can actually express this mathematically by noting that torque is always R cross F, and since the effective lever arm length of this dipole is L, the actual lever arm about the center is L over 2, but we have twice the charge that would otherwise be given by just one of these, so you end up basically having R cross F gives you P cross E. So P is the dipole moment, E is the electric field. And furthermore, you can get the potential energy for the dipole by taking the negative of the dot product between P and E. So the torque is P cross E, the energy is P dot E. So let's look at a few quick examples with that now. Okay, we begin with trying to find the dipole moment for a proton and an electron, like so, that are separated by a distance 0.100 nanometers. So recall that the charge for either one of these is about 1.6 times 10 to the minus 19 coulombs. Recall that 1 nanometer is 1 times 10 to the minus 9 meters. So the dipole moment P is going to be given by 1.6 times 10 to the minus 19 coulombs times 1 by 10 to the minus 10 meters. And so this looks like 1.6 times 10 to the minus 29 coulomb meters. Okay, second example, suppose that we place this dipole, the one that we just found, 1.6 times 10 to the minus 29 coulomb meters. Suppose that we place this into a field of strength 3 times 10 to the 6th volts per meter, and that the dipole is initially perpendicular to the field. Okay, that would give us some orientation that basically looks something like this. So therefore we can use that the torque is equal to P cross E. Since these two are perpendicular, that means that the magnitude of the torque is equal to P times E, and this sine of theta term basically is 1. So we have 1.6 times 10 to the minus 29 coulomb meters, and that's being multiplied by 3.00 by 10 to the 6th volts per meter. So this ultimately is going to give us a torque of approximately 4.8 times 10 to the minus 23 Newton meters. So the combination coulomb dot meter times volts per meter gives you coulombs times volts, which normally we rewrite as joules, but remember that a joule is a Newton meter, which is the proper unit that goes with a torque. So here's the torque for this combination. This last one is basically equivalent to saying what is the change of energy for this system. Initially, it's actually at the highest potential energy. Finally, it's at the lowest potential energy. So initially, the field and the perpendicular, the dipole are perpendicular to each other. So initially, we say U sub E is equal to 0 because U is negative P dot E, and the two are perpendicular. Finally, we have U E final, and that is going to be P dot E final. And this is negative, so that's negative of basically the P again was 1.6 times 10 to the minus 29 Newton, coulomb dot meter. And we're dotting that with the E field strength, which again is 3.00 times 10 to the 6th volts per meter. And finally, they're basically at equilibrium, and that means that they're parallel to each other. So that term is not 0; it's 1. Theta is 0. Cosine theta is 1. And so the final potential energy is minus 4.8 times 10 to the minus 23, and now we can actually use joule as our unit. Note that this is negative, whereas this is 0, so it's now at a lower potential energy than it was initially. So that means that it is at a lower energy state. It means that it will take work to rotate back from this state to the initial perpendicular state. Alright, so this brings up the two basic types of molecules that you can get with regard to polarization, one of which is a molecule that has a permanent polarization. So water is such a molecule. There's actually an asymmetry to the way that the molecule is built. So the center of charge is actually at this X right here. So that's where the center of charge distribution for the whole molecule is. It should be right below the oxygen molecule, which is effectively negatively charged, whereas the two hydrogens are effectively positively charged in this case. And the center of charge distribution is not within any one of these atoms in the molecule. You'll notice too that the molecule is bent, and by having this bend to it, it also has a permanent polarization. That means that if there is an E field somewhere, an external E field, this molecule will automatically line itself up by spinning to match the field. So for example, if the molecule is placed in an external field like this, then the molecule will begin to rotate until it has aligned along the fields. So the molecule started here. Basically, both of the H molecules are being pulled in this direction from left to right or to the right. The oxygen molecule is being pulled to the left here, and then the whole thing basically rotates until equilibrium is reached, in which case the hydrogens appear on the right side and the oxygen appears on the left side of the molecule. The other type of molecule that we can get with regard to polarization looks more like this. So everything is in the same plane. If there's no external field, then what happens is the center of charge is going to be sitting in this molecule. So you have a positive charge, negative charge, positive charge. So this atom and this atom are sort of the positive ion. This one's like the negatively ionized atom. And the center of charge for the whole thing is maybe somewhere here, near the middle of this one. Now you apply an E field, an external E field to this system, and what's going to happen? Well, the negatively charged molecule, atom, is going to get pulled against the field line. The two positively charged atoms in the molecule are going to get pulled with the field line. And so the molecule sort of distorts itself to look like this, so that these two are very close together. This one is farther apart, and you can see that there would therefore be some polarization to this configuration. Let's say this is +1, +1, -2. Effectively, this pair has a -1 to it. This is a +1, and so you have effectively a dipole again. So here's what's called an induced polarization. So let's now apply this to the case where a dielectric is placed between two plates in a capacitor. So here's our dielectric, and you'll notice that if any polarization exists, it's randomized. So this diagram works for both the permanent polarization case and the impermanent polarization case. It's drawn as if we have a bunch of polarized molecules, but even if we have unpolarized molecules, this still works because of the randomization of their orientation. So let's say that we take this and we stick it between two plates, positive charge, negative charge. Therefore, the E field looks from left to right. Well, this applies a torque on each individual one of these if they are a permanently polarized molecule, and if they're not polarized permanently, then it induces polarization, and either way, all of them end up aligning along these field lines, more or less, so that you end up with positive charges pointing more towards the right and negative charges pointing more towards the left. So what does that do? Well, effectively what it does is it decreases the spacing between the two plates in this capacitor. It's sort of like having a new plate that's inserted here very near to the positively charged plate that has a negative charge on it, and like having a new plate of positive charge very near to the negative charge. And so there's effectively two fields that are induced within or two fields, I should say, that exist within this capacitor between the two parallel plates. One is the initial field set up by the original capacitor itself, that is the delta V over delta X field. The second is an induced field, which is in the opposite direction and is of lesser magnitude than the initial field. Well, if delta V is given by E delta X, and if we use the superposition principle, you can see that by adding these two together, you get a much smaller electric field, and therefore you would get a smaller voltage between the two plates for the same amount of charge. Hence, you now have a higher capacitance. So let's look at that step by step in a little more detail. This is a more thorough description of how the dielectric modification works. You have initially your pair of charged parallel plates and your field. And if you want to move one charge from this plate to this plate, you have to do some amount of work. Or in other words, the electric field will do some amount of work if it's a proton that you're moving from here to here. That work is done by whatever charge you have times whatever field strength this is times whatever distance is between the two plates. That's this equation here. So now we insert a dielectric in between the two plates. Minus, plus, minus, plus, minus, plus. Everything's aligned along these field lines. What that does is you've got induced polarization for the symmetric material, or you have rotated polarization for the asymmetric material. Like water, for example, everything will rotate. And the orientation of the signs of everything within the material is going to be opposite that of the signs on the capacitor plates. And so what this does is it has the effect of eliminating some of the E field lines inside of the material. So you could think of that as having an induced E field like so that adds with the initial E field so that some of these field lines vanish. Recall that if a field line vanishes, what it implies is that you have a weaker field. So there's a weaker field here than there is here. The field doesn't ever quite disappear completely, I should add. So remember that the number of lines per unit area gives the electric field strength. By removing some of the lines inside of this, we've effectively stated that we are weakening the electric field here. So what that means is that if you're going to do some work to move a charge from one plate to the other, that the effective amount of work you have to do has been reduced because it's now Q times whatever remaining field you have times D rather than Q times E naught times D. So the work done is going to be somewhat less. Therefore, you end up with a reduced amount of work and hence a reduced voltage between the two plates. And this reduced amount of work and reduced voltage is thanks to the fact that you have this induced field inside of the material, which comes from the fact that all these molecules have rearranged themselves so that you have polarization lined up along the field lines. If you were to draw some field lines here, inside of the molecule, you'd have a field line from this point to this point. Then outside it'd be here to here, inside here to here, outside here to here. Well, these ones tend to be stronger because the charges are more close together. So you've effectively have a stronger field pointing this way than you do this way from the molecules themselves. That's where this induced field is coming from. So we can write basically that the effective field inside of the material is E naught, the original field caused by the pair of parallel plates, plus E induced, which is this induced field caused by the orientation of all the dipoles in the molecules making up the material. And so the effective electric field, we might write, since these are in opposite directions, the magnitude becomes E naught minus E induced. The induced electric field strength, in turn, is given by this formula. The induced strength is the E naught times 1 minus 1 over kappa. And recall that we actually used this equation right here earlier to figure out what the reduction in the potential energy was due to the presence of this dielectric. So since the field can be related to the permittivity of free space and the charge density on each plate, we can also note that the induced surface charge in the dielectric is given by this equation. So this is effectively how much charge is going to appear along each surface if we were to treat this as just being a material that has charges on the surface like a conductor. So as Q induced is Q times 1 over 1 minus kappa, just as E induced is E naught times 1 minus 1 over kappa. Alright, so I want to work through a few short examples here that have to do with inserting a dielectric between two plates, now with this description that has been given for why this reduces the capacitance. We begin with this question that says you have a parallel plate capacitor of initial capacitance C naught equals epsilon naught A over D. And we're going to insert into it a dielectric of constant kappa and a thickness F is less than D. So to draw this, basically you could think of it from the side as looking like this. So here is capacitor number 1. Maybe this is the positively charged plate of this parallel plate capacitor. Right here is the negatively charged plate of the parallel plate capacitor. Looks something like this. And then we decide that we're going to insert into this a dielectric material. And the dielectric material maybe is in contact with one plate, more or less, and comes out to here, something like this. So we have a thickness of F for this, but for the entire pair of parallel plates, there's a distance D separating the two. So how is it that we solve this? Well, one possible way to solve it, because I haven't really told you at this point how to go about solving for what happens if you have a dielectric whose thickness does not fill the entire space. The equations we've been working with so far have basically assumed that you've filled the entire space between the two plates. So here, by not filling it, we can do something like this. We can put in our positively charged first plate. Then we can say, suppose that we treat it by saying that here is the dielectric again. So again, this is thickness F. But we're going to redraw this pair because you can always draw a pair of otherwise identical parallel plates capacitors as being a pair in series. So the first one in the series looks like this, and the second one, therefore, is over here. So this is like having another plate inserted that has a sort of positive charge, and the separation between these two is now whatever D was minus the thickness of the original dielectric. So you have basically a pair of capacitors in series. you know that to find the equivalent capacitance, you basically use 1 over C is 1 over C1 plus 1 over C2. You know that C1 is going to be given by epsilon naught times A over F times kappa, because that represents the capacitance that you have for this first capacitor that has the dielectric in it. So this is now effectively a capacitor that is filled with a dielectric. This right here is C2, and C2 has no dielectric in it, so this has a capacitance of epsilon naught times A divided by D minus F. So now we need to basically solve by taking some reciprocals. So 1 over C effective is 1 over C1, so that's F over kappa epsilon naught A, plus 1 over C2, that'd be D minus F over epsilon naught A. So if we want to get a common denominator, that basically means that we have F plus kappa times D minus F divided by the kappa epsilon naught A term. Therefore, the effective capacitance, C effective, is the reciprocal of all this stuff. So we end up getting kappa epsilon naught A divided by F plus kappa times D minus F. And we could compare that to the initial capacitance of this whole capacitor. So this whole capacitor that just has two parallel plates and no dielectric in it, in other words, looks something like this, where the separation distance between the two is D. This would be C naught equals epsilon naught A over D. So if you look over here, you can see that you have an epsilon naught A over a bunch of stuff that doesn't look on first glance like there's a D in it. But it turns out we can rearrange everything in this equation so that this is equal to something like kappa over kappa minus F over D times 1 minus kappa times C naught. So that's what the effective capacitance is going to be when we put a dielectric partially into this system. Okay, the question is, suppose now that we're told that the dielectric is paper. Paper, for what it's worth, if you look back on that table, kappa is something like 3.7. And we're again placing it so that it's in contact with one side, not placing it in the middle. What you end up getting is basically C effective is equal, again, to kappa divided by kappa minus F over D times 1 minus kappa, and that's times C naught. So here is C naught, and here is F, and here is D. So we can plug all those guys in. C effective is equal to 3.7 divided by 3.7 minus, since these are both in millimeters, it's actually kind of okay to leave them unitless because the units will cancel. So 0.50 over 1 times 1 minus 3.7. And all of that is times 1500 nanofarads. So that's basically going to, when you plug all that into the calculator, it's going to give you about something like 2,360 nanofarads. What happens if we don't place this on the edge? What happens if we place it in the middle instead? Well, then effectively we end up with something like this. So here's the first diagram, like so. We are going to place into this first diagram a dielectric slab like this. So the distances given would be, this is basically d minus f over 2. This is d minus f over 2, and then this right here is F. And this basically breaks down into something that looks like this. First capacitor here, minus, 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 minus. Then second capacitor here, and this one is the one that actually has the dielectric slab into it, and then that's attached to the third capacitor, which is here. And so you end up having a setup like so. And again, here's where the dielectric slab actually lives. And so you end up with, if this is C1, here's C2, here's C3, 1 over C effective is 1 over C1 plus 1 over C2 plus 1 over C3. You'll notice that the values of the three capacitors that are created here, plus, this one has a capacitance because it's D minus F over 2. This one, the capacitance, we'll call it C1 prime, is actually equal to twice the capacitance of C1, where C1 was this one like so, and then separated by a distance of D minus F. So the equivalent capacitance here, 1 over C effective, is 1 over C, we'll call it C effective prime, is C1 prime plus 1 over C2 prime plus 1 over C3 prime. This one right here was, in fact, equivalent to the original C2 that we had. Remember, this is the dielectric filling the space between the two plates. C1 prime is 2C1. C3 prime is also, therefore, 2C3. So we can also write 2C3. So notice that this term right here is equivalent to 1 over 2C1. This term right here, 1 over 2C3, and C1 and C3 are equal, so we can actually write an equal sign in here. So if you add these two together, you end up with 2 over 2C1, and so you end up with, run out of space at the bottom, 1 over C effective prime is equal to 2 over 2C1 plus 1 over C2. And so that is 1 over C effective prime equals 1 over C1 plus 1 over C2 is the same as just 1 over C effective. In other words, by moving the piece of paper to the middle of the capacitor, we don't actually affect the capacitance. So it doesn't matter if it's in the middle or whether it's touching an edge. I wanted to finish out today's lecture video by working through a longer example. This one is sort of ties stuff together between the capacitor discussion and then our discussion in the light of having dielectrics. So I'm going to use, for this example, a lightning strike. And basically what we're going to do is take a given distance between the cloud base and the ground. It's about 1.5 kilometers, which is pretty close to the typical distance. It's within the range of distances that are typical. And we'll give it a specific charge for the lightning strike and assume that it's draining half of the cloud's charge in doing this. And so the questions are basically, what's the voltage drop from cloud to ground, or ground to cloud as the case may be? What is the capacitance of the cloud to ground capacitor? How much energy do we get in the lightning bolt? And if we have a given power for the lightning bolt, how much time does the lightning strike itself take? All right, to answer part A, we use that the dielectric breakdown for air, and again you should look this up in the table provided or in a textbook. The dielectric breakdown strength for air is about 3 times 10 to the 6 volts per meter. And we've been given a distance effectively delta X, if you will, or D, or if it's vertical, we might say delta Y or H, whatever. This is 1.5 kilometers, which is 1,500 meters. Recall that E is delta V over delta X, so delta V max in this case, the potential difference between the cloud and the ground before the lightning bolt arcs, is going to be delta X times E max, which is 1,500 meters times 3 by 10 to the 6th volts per meter. So that means that the maximum potential difference between the base of the cloud and the ground is about 4.5 times 10 to the 9th volts, so 4.5 gigavolts. B, we're given that Q discharge is roughly half of Q naught, and that is 15.0 coulombs that is being discharged. So this means that Q naught is about 30 coulombs. Remember that the capacitance is basically going to be Q over delta V. So we'll call that Q naught over delta V naught, where these V naughts and Q naughts maybe are more appropriately labeled with an I than a naught, since a naught is already being used to label what happens when there's no dielectric. So this right here is equivalent to the delta V max that we had above. So this is 30.0 coulombs divided by 4.5 times 10 to the 9 volts, which gives us an approximate answer of about 6.67, or with two significant figures, about 6.7 times 10 to the minus 9 farads. So that's the approximate capacitance of the clouds. For what it's worth, we could use this to also figure out what the area of a cloud is, because remember that C is going to be epsilon naught times kappa. A over D, kappa is approximately 1 in this case. So approximately 1, since it's air, that's the dielectric. And so A, very approximately, will be given by C times D over epsilon naught. So that's 6.7 times 10 to the minus 9 farads times the distance, which was given up here, 1,500 meters, divided by the epsilon naught, which was about 8.85 times 10 to the minus 12 farads per meter. So this gives an approximate area of about 1.130 times 10 to the 6th square meters. Or if we wanted to convert it into kilometers, basically it's an area of about 1.1 square kilometers. So the cloud base might be like 1 kilometer by a little more than 1 kilometer. Okay, next we're asked how much energy is contained in the bolt. And recall that the work done by moving charge off of a capacitor, or the total work to remove all the charge, is basically 1/2 of Q squared over C. We're going to choose this form of the work because the things that are changing here are the voltage and the charge, but the capacitance is remaining constant. So this is the best version because we are actually given the initial and final charge. So recall that work is equal to the change in potential energy, and then note that the potential energy, delta U, would end up being 1/2 of Q, basically final squared minus Q initial squared over C. And so work is equal to negative of this. Work is how much energy is in the lightning bolt. So this is energy in lightning bolt. And so basically what this lets us do is work is equal to 1/2 times C times basically the initial squared was the 30 and the final is 15. And so that means we could put in 1/2 times, so 6.7 times 10 to the minus 9 times 30.0 coulombs squared minus 15.0 coulombs squared. So we can plug all that into our calculators and get approximately 5.06 or 5.1 times 10 to the 10th joules. So that's about how much energy that bolt of lightning is carrying. Last but not least, we're given that the power is 1.21 gigawatts. That's 1.21 times 10 to the 9 watts. Remember that power is work per unit time. We're trying to solve for time, so time is the work or the energy divided by the power. And so therefore we can write delta T, this is the time that the lightning strike actually takes, is 5.1 times 10 to the 10 joules divided by the power was 1.21 times 10 to the 9 joules per second, since that's the equivalent unit to a watt. So the total time for this lightning strike would be a ridiculously long 41.8 seconds. So what does this tell us? Well, there's a variety of ways to look at this. Typically, the charge carried by one of these strikes is a bit less than the 15 coulomb number that I cited. But also, the typical power of a lightning bolt maybe is not 1.21 gigawatts. You can probably guess where I came up with that number for the lightning bolt power to be. But also this amount of charge being carried is a little on the high side. So that's all that I have for today's lecture. This one was pretty long because there were a lot of shorter examples interspersed throughout, but I hope that you found it to be a helpful lecture this time around, and thank you for watching.